Today we're going to talk about the shapes of molecules. Lewis structures are interesting and they're useful for telling us the arrangement of the electrons, the valence electrons in molecules, but they don't always give us the shape. In fact, a lot of the time they don't give us the shape. Here's an example of what I'm talking about. This is the Lewis structure for methane. We've drawn this before, I think. You can see that it looks flat. On a piece of paper or on the screen here, it looks flat. But in fact, this is the shape of methane. This is the carbon in the center, and these four H's are arranged in what you can see is a 3D arrangement. So the problem with Lewis structures is Lewis structures are flat, but real life, real molecules, are three-dimensional. Predicting shapes for a compound that only has two atoms in it is really simple. The only possible shape is linear. Here's an example of what I'm talking about. Nitrogen molecules look like this. There's the Lewis structure. It's only two atoms, and so it's going to be an N bonded straight to an N. It's a straight line. Predicting the shapes for compounds that have more than two atoms, well, that's a little more complicated. It requires a little more thought. The process that we use to do this is called VSEPR theory, and VSEPR stands for valence shell electron pair repulsion theory. You don't have to remember what all those letters stand for, but here's the basic idea behind it. Valence electron pairs are all negatively charged. Things that are like charged don't attract, in fact they repel each other. So all of these electron pairs, whether they're bonds or lone pairs that are attached to the same atom, they want to stay as far away from each other as they possibly can. And using that as a sort of a guideline, scientists have developed a whole set of shape predictions, and as our ability to test these increases, as technology increases, turns out that this theory is right most of the time. It's a very good theory. Let's apply it to this simple molecule. Here you see a Lewis structure of beryllium dichloride. With beryllium attached in the center to two chlorines on the outside, thinking about this electron pair, that bond, and this electron pair, that bond, as being repulsive to each other, because that's a pair of negatives, and that's a pair of negative charges as well. How far apart could they possibly be arranged in space to get away from each other? Well, the answer is 180 degrees. And so this predicts what we would call a linear molecule with a 180 degree bond angle. That's how the theory works. You look at the central atom, how many regions of electron density are surrounding it, and how far away would they have to be from each other to get as far away as possible. So the basic idea of VSEPR theory is that you're using repulsive forces rearranging themselves to predict the shapes of molecules. We're going to take a look at a few basic molecular structures. The basic ideas behind VSEPR theory can be put into about 5 or 6 different categories of molecular structures. Here's the simplest one. We just took a look at this earlier, and that's the linear shape that we saw with BeCl2. When you have two regions of electron density, two lone pairs or two bonds, the best they can do, the farthest they can get from each other is 180 degrees. And we see that here in this basic shape. 180 degrees is as far away as they're going to get from one another. This is another one. When you have three regions of electron density attached to the same central atom, the farthest apart they can get from each other is 120 degrees. And so they'll arrange themselves in a flat plane, and they'll arrange themselves where all the angles are 120 degrees, equal angles from each other. This is called a trigonal planar. Trigonal is another word for triangular, so some people sometimes just say triangular. And planar indicates that it's flat, it's in a plane. If you had 4 regions of electron density, they could arrange themselves in a tetrahedral shape, and this is the best that they could do. This is as far apart as these repulsive bits could get from one another. This is 4 atoms. If this is a molecule, there'd be an atom here, 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 and here. And all 4 atoms would be at the corners of, or the vertices of a tetrahedron. A tetrahedron is a 4-sided shape, almost like a pyramid. So this would be one of its sides, from there to there to there. Another one of its sides would go from there to there to there. Another one of its sides would go from here to here, back up to here, and then the 4th side would be on the bottom down here. That's a tetrahedron. And so this is called a tetrahedral shape. It turns out that the bond angles for a tetrahedral shape are all the same, and that angle is 109.5 degrees. That's the optimum arrangement that these things can get as far apart from each other in space as they can. If you had 5 regions of electron density attached to the same central atom, this is as far away as they could get from each other in three-dimensional space. It's called a trigonal bipyramidal shape. You can see where the name comes if you think about the points out here that would be atoms if these were all bonds, and the shape that they trace out. Here's a pyramid. There's one face of it. Here's another face of it. It goes from here to there to there. And then the back side has a face that goes from there to there to there. So that's a pyramid with a triangular or a trigonal base. But if you look downward, here's another pyramid that also has the same triangular base. So bi means 2, so it's a bipyramid that shares 2 pyramids that share a triangular base. That's where the name comes from. So the 5 atoms are at the vertices of a trigonal bipyramid that's bonded to a 6th in the center, and that's the black shape that we see in the middle here. Now, what are the bond angles? Well, it depends on which bonds you're talking about. We think of these 3 bonds and these 2 bonds as being in different locations. We give them actually separate names. And their names come from thinking about them as imposed on the Earth. Imagine a globe here. This is the axis of the Earth, and the equator goes like this. So these bonds are called axial bonds, and these bonds out here are called equatorial bonds, or equator bonds. Well, we already know what these are because we've looked at that trigonal planar shape, and that's basically what you have in the central plane. So in the central plane, these bond angles are all 120 degrees. Those are equatorial bonds. And then the axial bonds, the ones that go up and down from that central plane, well, they're at 90 degrees. So they're 90 degrees from the central plane, and these are called axial bonds. The most complex shape that we'll look at in this class is called an octahedral shape. This is when you have 6 regions of electron density bonded to the same central atom. If you, again, imagine these as all bonds, on the outsides of these electron pairs, we would have an atom, and those atoms fill up an octahedron. So that's an 8-sided figure. And this is kind of complicated to draw, so I don't think I will, but if you imagine all these points connected together, what you'd see is an 8-sided figure. This is sometimes also called a square bipyramid because it's 2 pyramids that share a square base, sort of like the 2 pyramids that share the triangular base of trigonal bipyramidal. Now, the bond angles are all the same. This is a symmetrical setup, and they're all 90 degrees. In all directions, they're 90 degrees from each other. So these are 90s here, those are 90s. 90 degrees everywhere. All bond angles are 90 degrees. So let's just summarize these basic shapes here. We've got linear, if these are all bonds to atoms, 2 outside atoms, 1 central atom, 180 degree bond angle. Then you have trigonal planar, a flat molecule, 1 central atom, 3 outside atoms, 120 degree bond angles. Then we have tetrahedral, 1 central atom, 4 outside atoms. All bond angles are 109.5 degrees. And then we have the trigonal bipyramidal. In trigonal bipyramidal, we have a central plane, an equatorial plane, that has 120 degree bond angles, and then these axial bonds are 90 degrees from that central plane. And then the octahedral shape has 6 outside atoms bonded to a central atom, and all bond angles are 90 degrees everywhere. It's a symmetrical structure. Sometimes all the electron pairs are shared pairs, they're bonds. Sometimes they aren't. Sometimes the electron pairs are lone pairs or unshared pairs. Well, here's how we deal with this. The first thing we do is draw the Lewis structure, and we use the Lewis structure as a clue to what kind of a shape we're going to have. We do that by counting the regions of electron density. Now, here's what counts for a region of electron density. A single, a double, or a triple bond counts for one region. Single bond is one region, double bond is a region, triple bond is a region. It doesn't matter if it's that stick, 2 sticks, or 3 sticks, it counts for one region. And an unshared electron pair is one region. That's not 2 regions. That pair of dots is one region of electron density. So those are the things that count as regions of electron density. And then you use the basic shapes that we just went through to dictate what kind of a molecule you have. The shape of the actual molecule is given by the locations of where the actual atoms are. But even in places where there aren't atoms, there are lone pairs sometimes, and that influences the shape of the structure. Here's an example. Water. If you look at water's Lewis structure, it looks like this. You might think, oh, straight line, H to O to H, be a linear molecule. But in fact, it isn't. This lone pair takes up some space. This lone pair also takes up some space. They're repulsive to each other, just like they're repulsive to the bonds. And so when you look at the actual structure of water, it ends up having a bent shape. Here are the lone pairs. These big green ears here represent lone pairs, and these are the bonds. So here's H, here's O, here's H. That bent molecule exists rather than a linear molecule because of the influence of these two repulsive lone pairs. Let's look at our first case. This is two regions of electron density with no lone pairs. An example would be carbon dioxide. Here's the Lewis structure for carbon dioxide. When we're making these shape determinations, we're always looking at the central atom. So we're looking at the carbon here, and how many regions of electron density does it have around it? And the answer is 2. There's one, there's the second one. So 2 regions of electron density. We saw when there are 2 regions of electron density around the central atom, this is going to be a linear VSEPR shape. And because there are atoms out here at the end, the molecular shape is also going to be what we call linear. So there'd be carbon here, oxygen out here, oxygen out here. Straight line molecule. There's another look at it. Carbon, oxygen, oxygen. All the molecules are all the atoms are in a straight line. Bond angle 180 degrees. Another way that you can think about this is with a kind of a coding system. If you have a hard time visualizing these things, but you're better at memorizing things, well, you might think about this as an AB2 molecule. We'll go through here and insert this code in all the examples that we work through. The A always means central atom, B always means outside atom. And then we'll start to introduce lone pairs, and those will be E's as we go through this code. So an AB2 is a linear. The next most complicated setup we could have is 3 regions with no lone pairs. An example of this would be BCl3, boron trichloride. If you draw the Lewis structure for that, it looks like this. And if you look at the central atom, the central boron, it's surrounded by 3 regions of electron density. So that would make the VSEPR arrangement a trigonal planar. That's one of our basic shapes that we went through. The molecular shape is also trigonal planar because at the outside of each one of the regions of electron density, we actually have an atom. So there's boron in the center and chlorines on the outside. Bond angles are 120 degrees. It's a trigonal planar molecule as well as a trigonal planar VSEPR arrangement. Here's the shape again for the example we worked on. Boron in the middle, chlorine are the outside atoms. Okay, now we're going to look at 3 regions where there's 1 lone pair. So now we're talking about this is a pair of electrons. It's not really a bond. And then this will be a bond to an atom. An example of this would be the nitrite ion, NO2 1-, which has this Lewis structure. Now, if we look at the central atom here, the nitrogen, we've got 3 regions of electron density. Here's 1, the lone pair is 2, and the single bond is 3. So that means the VSEPR arrangement is going to be a trigonal planar, just like we had in the last example, 3 regions of electron density. But the molecular shape is going to be different. This bond angle is going to be approximately 120 degrees, maybe a little bit less because electron lone pairs tend to spread out more and they're more repulsive than regular bonds. So it might squish this in a little bit less than 120 degrees. But it's a bent molecule, and so the name is called a bent 120 because of the bond angle. We're going to see later that there's another bent, so we have to use that to distinguish. So this would be a picture of the molecule itself. Here's a lone pair, and in the example we were using, this is a nitrogen, this is one of the O's, and this is the other O. That bond angle is 120 degrees, bent 120 molecule. Well, next we're going to look at examples where we have 4 regions. First of all, we're going to look at 4 regions with no lone pairs. An example of this would be methane, CH4, and the Lewis structure for methane we saw earlier looks like this. So looking at the central carbon, we see 4 regions of electron density. 1, 2, 3, 4, all in bonds. Well, that means the VSEPR arrangement is tetrahedral. And the molecular shape is also tetrahedral because all of these regions of electron density are actually bonds. So you get the carbon in the middle, and then there's atoms on the outside of all of those little green ears. This is a look at what the molecule would look like. For the CH4 example we were looking at, there's C, and each of these outside atoms are H's. Let's take a look at a case where there are 4 regions of electron density, but one of them is a lone pair. An example would be ammonia, NH3. The Lewis structure for ammonia looks like this. Looking at the central nitrogen atom, I have 4 regions of electron density, a lone pair and 3 shared pairs, 3 bonds. So that means my VSEPR arrangement is going to be, again, tetrahedral. The molecular shape isn't. This is now a lone pair. I've got a bond here, I've got a bond that kind of angles down here, and I've got a bond that kind of angles down here. These 3 bonds, if you think about it a little bit, well, they make a pyramid with a triangular base. And so this molecular shape is called a trigonal pyramidal, triangular pyramid. The actual shape of the molecule, here's my lone pair. Using the example that we had, there's nitrogen, hydrogen, hydrogen, hydrogen. Now let's take a look at 4 regions with 2 lone pairs. An example of this would be water, H2O, that we looked at earlier. Water has this Lewis structure. The central oxygen has got 4 regions of electron density, 2 are lone pairs and 2 are bonds. Well, since there are 4 regions of electron density, again, it's a tetrahedral VSEPR arrangement. The molecular shape is different. This would be considered a lone pair now, and maybe this would also be considered a lone pair. And so I've got a bond coming up here, got a bond coming down here, and the angle between here, if this were tetrahedral, should be 109.5. But because we have 2 of these much more repulsive lone pairs, that actually squishes this bond angle down quite a bit, and it ends up being a 105-degree angle. So we name this thing a bent 105. That's the name of this molecular shape. So there's water, oxygen in the middle, 2 H's, and those H's are in this 105 angle configuration.